So now in this video, we're going to look at RC time constant right there. So there's a distinct curve. We'll look at that on the oscilloscope when you charge the capacitor. Mostly the voltage shoots up rapidly at first and slowly rises over time. But in any case, we are going to have a switch. I'm just going to use a jumper actually to short the capacitor, keep it discharged. But when we yank the jumper, open the switch, then the capacitor will start charging through a resistor. So the resistor sets the current based on the capacitor voltage and the voltage of the power supply. But larger value capacitors need more current to raise their voltage than lower value ones. So I got a pictorial there and schematic over here. Different value components though. So we're going to use 1000 microfarad there. Here's a 100 microfarad capacitor, so 1/10 the capacitance, but 10 times the resistance of what we got there. So the timing should equal out really nicely. And these components are not high precision, especially the capacitors, so they may vary a little bit. But for the most part, we're going to get really close to 1 second. So you take the RC time constant, so you could either have TC for time constant or the Greek letter tau, which just looks like a T with this font, but it's the Greek letter tau. It means the same thing as time constant, and it is in seconds. And so it's just resistance times capacitance. So the capacitance is in farads. So 1000 microfarad is the same as 0.001 farad, which is the same as a millifarad, but for some reason capacitors just go into thousands of microfarads instead of millifarads. So in any case, we got that times 1000. So that's 1/1000th times 1000. It's 1. And since it's time constant, it's seconds. The 100 microfarad capacitor here, that's 0.0001 farad, so 1/10 the value there, and then times 10,000. So 1/10,000th times 10,000 is equal to 1 again, 1 second. So what that 1 second means is 63% of the remaining voltage. That's what will change. In this case, we are charging it. So we'll look at that on the graph, but that means you get a big voltage change at first. There's less voltage difference for the next time constants, and so they change about 2/3 what's less. So there's less voltage being changed each time constant. After 5 time constant, there may still be a little current trickling or whatever, but you still consider that to be, in this case, when the capacitor is totally charged. So the capacitor has a couple of plates with the insulator in between them, and those plates build up charge as current flows into them. As the plates get opposing charges, they build up a voltage, and then once they get to the supply voltage, it stops letting current go through. Then you got equilibrium. So in any case, that's topics for other videos. We're going to zoom back and actually look at the curve for now. So I paused that from earlier filming. I'm refilming this, but in any case, we can take a quick look at the power supply right there, 7 volts. And so we're good to go. The oscilloscope has a cable that comes out to alligator clips. I clipped them to jumpers right there so that we can easily move the jumpers to take a voltage measurement. So I can go right to the capacitor or anywhere along ground, the 0 volt reference point there, the negative side of the power supply. So I'll go right next to the capacitor. Why not? And we'll do the same up there. And you can see that we got 7 volts right now. So I'm going to just use a little jumper to discharge the capacitor, the same as being a closed switch, once I get into the right spot there. And you'll see the voltage suddenly go to nothing, but when I yank it, then we'll see the RC time constant. So 1000 microfarad and 1000 ohms, and I will zoom in so we can get a little better look and try to get it right on the line. So I should have waited just a speck longer, but we're pretty close. You can see if we go just a little tad bit before that line, we're about 2/3 of the way up, and then the next second about 2/3 of the way up. So 1, 2, 3, 4, 5 total seconds. I think I went 1 too far. Yeah, so in any case, you can see we're pretty much fully charged right there. It's not exact precision anyways, but it looks like we did pretty good. So now we're going to yank the 1000 microfarad capacitor, and first we'll do the 100 microfarad capacitor. Looked like it already had 7 volts on it. I didn't discharge it when I yanked it out, it looks like. But in any case, we'll discharge it now. So this is still the 1000 ohm resistor. We expect the voltage to change about 10 times faster, approximately. So we yanked that, and there you can see, it just shot right up. So we couldn't see the curve on there. And at the settings, we got the oscilloscope right now. So this is 10,000 ohm resistor. It looks like it was starting to self-discharge over time, but now it's charged, and we will put the discharge in jumper. And we already saw everything going on over there. We'll just zoom in, and I mostly looked at the oscilloscope as I yank the jumper. We're pretty much done now. So there you can see the curve. Looks like pretty much the exact same curve that we had before. I can pause it. There we go. I think I got the line pretty much spot on. So there you can see we went up about 4 volts again. That first time constant, somewhat close to about 2/3, about 63% or so of the total change. So not exact, not precision, but close enough for this video. You can see it's taking about 5 seconds to get fully charged. So I hope you enjoyed the video. Make sure you check out the other ones I'm posting in the screen. And check out the links down in the description. They all help out a ton. I will see you in the next video.